Evening. This is Dr.M.L.N.Acharyulu, Professor, Department of ECE, St. Peter's Engineering College, Hyderabad. Today we are going to talk about the horn antenna. Before the horn, why we are going to take a horn antenna generally? So the classification of antennas already know that. So here the aperture antennas. So aperture antenna have the radiation patterns gives in a omnidirectional. So therefore it is a non-directive radiation patterns. So which is not up to mark to give a directional patterns. So now we are going to talk about the horn antennas. What are the drawbacks? The VSWR is increases in that aperture antennas and it gives the poor radiations. But this type of antennas is applicable in only in the surface search radar applications. But in the horn antenna have a lot of applications in the communication area. So we are going to talk about the basic of the horn. Horn is a flared out waveguide generally, right? So here, this is the horn antenna. The horn is nothing but more than the hollow pipe of a different cross sections, which has been the tapered, the flared out. I mean, tapered or flared or whatever, both are same, to a larger openings. The type, direction, and the amount of taper, the flare, can have a profound effect on the overall performance of the element as a radiator. So here, generally, so the energy of the beam slowly transformed into radiation through the taper region, that is an antenna. Just you will coming to the antenna, the electrical signal should be transformed to the electromagnetic wave by using of the antenna. So here the flared out waveguide, right? So here the losses are reduced and the focusing of the beam improves. And a horn antenna may be considered as a flared out waveguide, already know that. So by which the directivity is improved and the diffraction is reduced. Okay, that is the main thing of the main function of the horn antenna. And the horn antenna may be classified in the different forms, like you say that the E plane, H plane, and the EH plane, which is nothing but a pyramidal horn, and the conical horn, biconical horn, like this. So this is the four types of horns generally. So the E type horn, E plane horn is like this. The electric waves, which is a vertical polarization, and the H plane horn, which is the horizontal polarization. This is a pyramidal horn. So EH plane, you say that. This is a conical horn. So now the horn is widely used as a feed element for the large radio astronomy. So what is the reason why we are using this horn? The horn antenna gives the maximum efficiency, near to 80% efficiency. That's why these horns are used as a feed points, feed antenna to the parabolic reflectors generally. The parabolic reflectors are used in a satellite communication. So therefore, this horn is used for the feed element for a large radio astronomy. That is the first application. And as well as satellite tracking also, we use the horn antennas. Communication dishes installed throughout the world. Communication dishes all will be built with the horn antenna. Feed for reflector and lenses. Just now I told the reflector antennas, which is the feed point is horns, because it gives the maximum efficiency compared to the dipole antennas. So it is a common element of phased arrays. Arrays, already know that radar is there. In the phased array radars, we use the common element for all phased arrays. And serves as a universal standard for the calibration and the gain measurement of other high gain antennas. This is also very good application, which is the measurement of the antennas, generally used to take horns only. So it's a widespread applicability stems from its simplicity in construction, case of excitation, versatility, as well as a large gain and the preferred overall performance. These all are the advantages. So what is so many applications is there by using of the horn antennas. So what is the simplicity, first thing, in a construction wise? If you're coming to the good excitation of the energy and the versatility, the shapes also, and the large gain will be very high. That's why we use the feed point for all microwave antennas. They prefer the overall performance also. So the impedance, horn input impedance is slowly varying over the wide frequency range. So here generally used to take a sectorial horns. This is the one type of horn, like you say that the E plane or H plane horns flares out in only one direction, that is called. The flaring in the direction of the electric vector produces a sectorial E plane horn, and similarly you say that the flaring in the direction magnetic vector which produces the H plane horn, that is, and the combination of these two, that means E and H horns combined and will get the pyramidal horn, that is called the pyramidal horn. The type of horn has flaring on both sides. So if the flaring is done on both sides E and H, so therefore the E walls of the rectangular waveguide, then the pyramidal horn is a produced antenna has the shape of the truncated pyramid. That is the pyramidal horn antenna produces the signal. Similarly, you say that the conical horn, fourth type, that is, when the walls of the circular waveguide rear flared, this is that is known as the conical horn. It's a logical termination of the circular waveguide, you say that. Okay. So the four types of horn antennas, and what is the flexibility, what is the advantage, what is the application of the horn antenna, already we know that. Now we will come into this impedance. The antenna impedance is represented as the ratio of voltage to current at antenna terminals. Already know that how we are going to find the input impedance or the output impedance. This is the ratio of the input voltage to the input current is the input impedance. So at the terminals, either input side is the input impedance, if we will consider the output side, the output impedance. In order to achieve the maximum energy transfer, input impedance of antenna must identically match characteristics impedance of a transmission line. Generally used to take the input impedance of the line which is equivalent to the characteristic impedance. So the line will be matched. Therefore, the maximum power should be transferred. If the two impedances don't match, the reflected waves will be generated and travel back towards the energy source. That means, if the terminating impedance is not equivalent to the generator impedance, you say that load impedance is not equal to the generator impedance, or which will be not equal to characteristic impedance, then what happened? The mismatch between the impedances is there. So therefore, incident and reflected waves both will be formed, and the standing waves will occur. So therefore, the energy should be lost. Ultimately, the efficiency of the antenna is reduced. So that is the main intention. So here the impedance matching is very important. For example, impedance matching of an antenna with no load attached, if we will say consider the ZA equal to RA plus JXA. This is the with no load, where ZA is the antenna impedance, RA is the antenna resistance, and XA is the antenna reactance, which all are in ohms. Z equal to R plus X, like that. So therefore resistive part we will consider here. The resistive part, antenna resistance is the combination of the radiation resistance and the loss resistance of the antenna. So RA equal to RR plus RL, already know that. The input impedance of the antenna is a function of frequency generally. Thus antenna will be matched to interconnected transmission lines and other associated equipment only within a bandwidth. In addition, impedance depends on the factor like geometry, it's a method of excitation, and the proximity surrounding objects. So therefore, the impedance is generally depends on all these factors like geometry and the method of excitation and the proximity surrounding objects. So here, just you observe that either the transverse electric or transverse magnetic waves. Transverse electric or transverse magnetic waves. If you consider the transverse electric wave, j omega mu by gamma mn. So here already know that which is equivalent to the eta by under root over 1 minus fc mn by f whole square. That is the frequency, critical frequency of the m and n modes, which is by the operating frequency. So here this is for the ZTM, the This is the impedance of the TM wave, that is the TM wave impedance, which is indicated with ZTM, gamma Mn by Z omega epsilon, which is a little bit reverse of that. So eta into of under root over 1 minus Fc by F whole square. This is about the impedance of the antenna and the polarizations generally. The polarization of the antenna is the orientation of an electric field of the radio wave with respect to the Earth's surface and is determined by the physical structure of antenna and its orientation. Generally, what is the polarization? You say that the electric field orientation in a particular direction, that is called the polarization. Either the polarization may be considered the linear polarization, elliptical polarization, circular polarization, which is again depends on the axial ratios. If the axial ratio equivalent to the 1, then that is called the circular polarization. If the axial ratio is more than 1, that is called the elliptical polarization. If the axial ratio is infinitive, it is called the linear polarization. So that is the polarization things. And the straight wire antenna will have a one polarization when mounted vertically and the different polarizations when mounted horizontally. If we will coming to the reflection, generally affects the polarization. For radio waves, the most important reflector is ionosphere signals, which reflects from it will have their polarization changed. So this is the one is the electric field orientation will coming. Otherwise, another the wire antennas will be mounted on one polarization when mounted on vertical, when the different polarizations mounted on horizontally, and the reflection will be effect on the radio waves. Most important reflector is ionosphere reflections and all. So this is about the polarization. The polarization of a radio wave is defined as the property of the electromagnetic wave describing the varying the direction, the relative magnitude of the electric field vector. So here you observe that the three types of polarization already I told. The same thing is replica here. It is described by the geometric figure traced by the electric field vector upon the stationary plane perpendicular to direction of propagation as a wave travel through the plane. If you coming to this, the linear polarization is vertically polarized, and it is a circular polarization, the Ex equal to Ey, and elliptical polarization, Ex is not equivalent to the Ey. So this is about the polarizations of the antenna. The vertical and horizontal polarization is the simplest form. They fall under the category of linear polarization. Already I told. Circular polarization. The two or more linear polarization waves add together such that the E field of a net wave rotates. Its advantage, it helps to overcome the effects of the propagation anomalies and the ground reflections and the effects of the spin that occurs on many satellites. This is the advantage of the circular polarization. It reduces the reflection effects. And the elliptical polarization occurs when there is a mix of the linear and circular polarization. That means the circular polarization Ex equal to Ey, but elliptical polarization Ex is not equal to Ey, but it is a perpendicular to each other. And next, the radiation field. The waves of the signal will propagate down the horn antenna towards the aperture. As they travel along the flared opening, the waves travel as a spherical wavefronts. Its apex is referred to as the phase center of the horn. As the phase front progressing along the horn antenna are spherical, the phase increases smoothly from the edges of the aperture plane to the center. The difference in the phase between the center point and the edges is called the phase error. What is the difference between the center point and the edges? The phase difference will be, that is called the phase error. This increases with the flare angle, reducing the gain. If the flare angle should be increases, then the gain should be reduced, but increasing the beam width. What happened actually? If the flare angle is reduced, flare angle will be increases, then the gain should be reduced, but beam width should be increases. As a result, the horn antenna have a wider beam widths when compared to the similar size of the plane wave antennas, like a parabolic reflectors and all. And in order to provide a narrow beam width, a longer horn is required, that is having the smaller angular flare to keep the phase angle constant. If we will say the narrow beam width is there, a longer horn is required for this, and the flare angle will be very small here. So what happened actually, flare angle will be very small, then gain increases, but the narrow beam width will get. If the other case, if the flare angle is increased, then the gain will be reduced, but the beam width should be wider. So this is a little bit different to that. However, the phase errors issues means that the horn size are practically limited to around the 15 wavelengths, that is only 15 lambda knots. Otherwise, the larger size would be required as much longer antennas. So, what is the limitation here? The phase error issue however, the phase error issues mean that the horn sizes will be practically limited to around only 15 wavelengths, not more than that. Otherwise, we may construct a larger, longer antennas. So here, this limited gain of practical horns is about the 30 dB isotropically. So, and the minimum bandwidth is to 5 to 10 degrees. So here, this is the gain, how it should be changed. Like this, the radiation pattern of the 2 gigahertz is shown in the figure. This is the practical antenna. And for example, you say that the A is equal to 3.69, B equal to 1.64 inches, A is equal to 3.69, B equal to 1.64 inches, A equal to 30 and B is equal to 30 inches. This is an example given. The horn is somewhat large and will work well above roughly the 2 gigahertz. Horn made for the higher frequency or the smaller. This horn antenna with a waveguide feed is shown in the figure. Just to see, here it is the A length. What is the A and B here? And this is the size of the horn antenna. We're constructing like that. If you're coming to the gain, horn antenna have a very little losses. So the directivity of the horn is roughly equal to its gain. So the maximum gain will get. Then the directivity is approximately equivalent to the gain. For an horn to be realizable, the following must be true. So resistance of the E sectorial equal to the resistance of the H sectorial is equivalent, right? And which is equal to RP. Just to observe that, so here the R naught H by RH is equal to A by 2 by A by 2 minus A by 2. This is completely depends on the geometry, A by A minus A, right? So R naught E by RE equal to B by 2 by B by 2 minus B by 2, which is equal to B by B minus small b. So that is you say that the apertures, A is A and B, capital A and capital B are the apertures. And the mouth, what is the sizes A and B, small a and small b's. So therefore here, which is for the H sectorial have mouth size is small a and the aperture size is capital A. And for the E sectorial, you say that the small b is the mouth size and the aperture size is B, capital B. So therefore, you used to take RE and RH will be, consider that RE and RH, the relations is A by A minus A and B by B minus B respectively. So now this is the H sectorial and E sectorial horns. So now the optimum gain condition. According to that, you say that B square minus BB minus 2 lambda RE equal to 0. This is the E plane condition. So here from that relation, you applied that AX square plus BX plus C equal to 0. That formula you can find the roots by using of that. Then there is only one physical meaningful solution. We'll get like this: half into half B plus and a root over B square plus 8 lambda RE. So similarly, you say that the maximum gain condition for the H plane, which is also same, RH is equal to the A into of A minus A by 3 lambda. And similarly, RE is equal to RH. Therefore, you say B is equal to half into half B plus under root over B square plus 8A into A minus A by 3. These the very optimum gain conditions for the E sectorial and H sectorial horns. The combinations will give the pyramidal horns. Substituting in that expression, and we'll get the gain of the horn antenna. So G is equal to 4 pi by lambda square into epsilon AP into A into B. So therefore, the relation between the A and the horn aperture of the H sectorial and aperture of the H sectorial and what we call the gain of the antenna system, which is depends the relating equation is like this, and the aperture efficiency also there, epsilon AP. So now you say that the isotropic antenna what is given and the horn antenna what is given. Just to observe that the shape is like this, the isotropic antenna which gives the radiation 360 degrees. And here you just to say radiation pattern which is the complete 360 degrees, but here the horn antenna which gives in a particular direction, just like this. This is the gain over the isotropic is 0 dB, but here the 15 dB. Beam width 3 dB is a 15 here, like this. So lower beam width. Gain, beam width and radiation pattern of a horn related to the isotropic antenna is shown above chart. Just to observe that, you can find the horn antenna have a excellent advantages over the isotropic antenna. So this is about the horn antenna. It's